Today I will talk a bit about our approach at Flanders Make to modeling and system identification. But first, yeah, there is this slide on the practical guidelines, so you should all be muted in order with this big room of people to not disturb the talk. And you can, if you have questions, put them in the chat box or ask them directly at the end by raising your hand. The meeting will also be recorded, so if you have to leave early or you missed it today, then you can see it afterwards on the recording. So let me begin by maybe explaining what the title was all about. So what is the physics-augmented machine learning that we are talking about, and what are the motivations for it? So a typical case, or what we will discuss today, is you want to model some aspect of a production machine or some mechanical system or thermal system or anything on your production floor, and you want to do that by doing some experiments and then constructing a model, maybe for control, maybe for some other reason. But what is typically happening is you do a limited data campaign, and then you can find a model that works well in the conditions it was tuned on. But once you go then to different operating conditions, you notice the model does not perform that well. And that is because you typically have a limited amount of data. And limited data leads a bit to trust issues in your model, because I did not test all the conditions I wanted, or that can ever happen. So can I really trust the model in those conditions? So what is the typical next step? Well, you just need to give it more of those unseen conditions. But very quickly you notice that I have all these aspects to take into account, many different parameters that can change or conditions that can change, and it quickly explodes into a very big amount of combinations that you need to test. So because it's such a big space of combinations, typically you do not test all of them because it would just take too long, and you end up with an undersampled experimental campaign of all these conditions. So how can we solve that is what we will talk about today. And if you then don't know which experiments you should perform next to improve on the trust in your model, and how can you know which experiments to prioritize over all these other combinations that exist. So we do have some positives. Let's say you have some physical knowledge or knowledge about your system. This is something we can exploit. Or if you have a very similar system or machine somewhere around where you did already do this exercise for, then it's also a big benefit which you can exploit. And then to put some buzzwords on it or some techniques behind it, at Flanders Make, we've investigated some solutions for these problems, and one of the solutions we call physics-augmented neural networks, which is our approach to physics-informed machine learning, let's say. This will allow you to leverage your intelligence about your machine. Transfer learning is, I think, well known in the machine learning community. So you start from a similar model or system, and you leverage the previous effort you put in that model for a new model. And then uncertainty quantification will help you deal with your trust problems in the model, and also can help you to guide your experiments. And today I will talk mostly about the green and the blue aspects here. So let's just dive into it. But first, this is all in the setting of physics-augmented neural networks. So we should talk about them. What is it? And it's actually quite simple. So, but a bit of background. If you want to model something with a model, you would have in the past typically two approaches. You write down some physical equations and so things like the laws of Newton or some simple thermodynamic laws you find in big textbooks and so on. And these are then your physical model. There are, of course, still some unknown parameters in those models, typically, like the exact mass or the exact density, things like that, that you still need to fine tune with a little bit of data. And then the other approach is fully data driven. So there you don't put in any physical knowledge, but you just use machine learning models with lots and lots of parameters and tune those parameters to do basically function approximation. Well, now more and more in literature, you notice that people are combining the two. So how can you use your physical insight you have about your system together with these data-driven techniques? Already for quite some years, this has been a hot topic. And in all those different formulations of combining them, we have found, or we have been using one of it more than others, and that's what we'll be talking about today. And this is called physics-augmented neural networks. And to go immediately to a use case to show and not keep it very dreamy what it is, I'll introduce this case of cooling power electronics. So this is a setup we have in one of our labs where this is used to cool a certain component, electronic component that generates a lot of heat. It needs to stay at a constant temperature, and we want to do model-based control of this temperature. And it needs to work in different operating conditions. So the heating power, or the heating of the electronics can change. The flow rate of a cooling liquid along this component can change, and the channel geometry can change. And what happens really on the microscopic level is a bit out of scope. For a model that is to be used in control, we cannot do computational fluid dynamic simulations. So we need to approximate it, and therefore a 5-point lumped parameter model is constructed. But why do we need these physics-augmented neural networks? Well, because it is quite complex what is happening actually, the cooling behavior. So near the boundary layer between the liquids and the base plates, there are some complex hydromechanics happening. So you start from a quite turbulent flow, and then depending on the flow rate, it is developing into a stable developed region or laminar flow. So this is all quite complex, and there are some physical laws available in textbooks, but there's no one fits all solution unless you do like a very detailed simulation. So what we do is we have these 5 points along the channel where we want to estimate the temperature. And you might know that for thermal systems, it's often a good idea to approximate them by an electrical analogy. So call it then thermal resistances. And we then know that, okay, the power you put in needs to flow through these thermal resistances, and eventually the liquid will heat up. And then, as I said, the difficult part is the interaction between the base plate and the liquid. So we also put the thermal resistance there, but instead of it being just a simple value, it is a value that will change for every for different operating conditions. And so what is now the key thing that we do for physics-augmented neural networks is, for this difficult to model aspect, we just replace our original parameter by the parameter and adding a neural network model to it. And then we can still choose what the inputs to that neural network should be, but we replace our difficult quantity, our difficult physical parameter by the original estimation of that parameter plus neural network. So here it is the thermal resistance between the liquid and the base plate. Okay, and then you get these kind of equations, but the equations don't matter that much. So that was a quick example of what a PAN model does. So when could you use this kind of approach? Well, when there's limited available data for a full black box model, because in the end it will have a lot more parameters. If you do have a physical model available to exploit, so let's say 50% of the model is actually physical equations, the other half will be captured by this neural network you put in there. And when you know that the problem is so difficult that you would need a lot of expertise to accurately model it with physical knowledge, then this is also a good approach, because you can do it a quite basic modeling and then take the final step with this data-driven neural network approach. What are the results you can expect from this? Well, you can expect a better model for less data. So that's already at the title of the talk, leverage the limited amount of training data. You can expect better extrapolation behavior because your physical laws are still in there, and the extrapolation then will also have these physical laws in them. And you can use this approach to iteratively improve your physical model by analyzing what the neural network is then doing. So that will be the missing components in your physical model. Okay, so that was a very short introduction on the PAN models. Let's now go to the uncertainty quantification. So at this part is, I repeat, when you don't trust your model into new conditions, and when you don't have an idea on which of experiment should I do first to improve my model the most. So when we talk about uncertainty, it needs also a little bit of introduction. So let's start with a simple example. We have here a one-dimensional regression problem. So we're just trying to fit a line through these black dots, which are data points. And if you then add uncertainty to your prediction, what you will typically see is this kind of plot where we have this uncertainty band around it. And we intuitively know that it will be a little bit bigger in between the data points. And if the data itself is noisy, there is also some effect. So what does that now mean if we take a cross-section at one of these points? So it's one-dimensional. X is just a one-dimensional value, and f of x is also a one-dimensional value. But still, we can make it complex. So at this point, we can consider two distributions. One we can call the model uncertainty, another one the intrinsic uncertainty. And the model uncertainty, you can look at it from two angles. So if you know about the Bayesian view on statistics, then it can express the belief of your current belief of where the function should be. And if it's very wide, then you're very uncertain. If it's very narrow, this distribution, then you're very certain of where it is. On the other hand, you could also see it as an empirical distribution. When you do a training of a neural network, every time you get a different outcome. And why is that? Because you have some random initialization of the weights. And so you always take a different path to your final point. So there is actually a spread in the solutions you get at the end. So you could also see it as the empirical distribution at the end of training. So not always the same. And if you do that, you notice that the variation is of course higher in between the data points, because there the cost function is not affected by this big change. And where there is data points, yeah, there the cost function will go up very high if you deviate from the optimal function. And then the intrinsic uncertainty, this is actually just a distribution of the data. So there can be sensor noise or process noise or just some stochastic behavior in your system, which means that all the data points will not be on a straight line, but there will be some noisiness to it. Typically, this also means there is some microscopic or macroscopic effects that are not in the model you're considering. So in order to draw this line, you need to decide what are the inputs and what are the outputs. Basically, if you consider all the other parameters that could be inputs, you don't consider them, they might lead to some noise. Okay, and then what happens typically under some assumptions, if you add more data, this purple distribution will get more narrow and will shift hopefully to the middle of your intrinsic uncertainty. So that's why we know that's a good idea to gather more data. And then why am I telling you all this? Well, we can actually quantify the width of these two distributions, so the model uncertainty and intrinsic uncertainty, with some methods. For model uncertainties, for example, ensemble training or the Laplace approximation, but there are many more. For intrinsic uncertainty, we can do this with probabilistic neural networks. But the key thing is you can get out the widths of these two distributions and use them very usefully, and that's what I will prove next. So we can use the model uncertainty for guiding our experiments. And for this, I will come back again to this power electronics cooling case. So a reminder, we are trying to estimate the temperature at 5 points along the channel. And we have two controlled inputs, the flow rate and the heating power. And then we have some other uncontrolled inputs like the ambient temperature, the inflow temperature, and the channel geometry. You might recognize in the signals I'm plotting here that we did a small data campaign, and it's taking these steady state steps. So that reveals that we did a sort of a uniform grid sampling. Now the experiment we will do is, can we do better than a uniform grid sampling? So we have research is approached based on the model uncertainty to come up with optimal experiments. And how we do that is here in a simple scheme. So we quantify the model uncertainty, we simplify it and make a sort of approximate model for it with the Gaussian processes. And then we do an iterative greedy optimization. And then we now try to compare the optimal data set according to these methods to a graded data set which has the same amount of points. And then you can make these kind of curves. So what do we see here at the top? It is the error, the mean absolute error on the temperatures. So remember, the temperature was what we try to predict, and we do that for each point in the input domain. So we have a two-dimensional input domain. That's why we see in the square all these dots. And if we have in the training set only 4 points, then we can plot a score and we say, we have an error of, what is it here, 0.55. And then if I add more and more points, all the way up to, I think it's about 58, then yeah, of course, the error is a lot lower. And we see that the blue curve, which is the one with the optimal data set, achieves a lower error earlier than when we do the gridded data set. Okay, so we are happy. Our optimal experiments seem to be better, but it is actually a bit of a surprising result if you think about it. How can a gridded data set not be optimal because it's optimally filling the space of the square. And this is actually where it becomes interesting. So because we are using this kind of PAN model, remember the neural network was all the way deep down somewhere in the equations. And this means that each point will be informative to the parameters of that neural network, but not in the same way. So if the neural network has no effect, for example, here on the bottom right, then if you add more points there, it will not be an informative point for the neural network parameters because it cannot change its prediction there. So points are actually more informative at the top left than at the bottom right. So this sort of imbalance of how informative the points are leads to this result that actually it's good to optimize instead of just doing a uniform grid sampling, which shows us that even for seemingly simple problems, it's good to make it explicit what is informative and what is not. And in this case, because we have a lot of neural network parameters and some physical parameters, more points are being added here to the top left. Another thing we could do with this uncertainty quantification is help with the problem that we don't have trust in our model. And for this, I will introduce another system that we also have in one of our labs. And it's a simple slider crank mechanism that occurs in many machines somewhere. For example, in a weaving loom, you might need to have some reciprocating motion. And it all needs to be very high performance because everything is running very quickly. So it's a common mechanism to convert a rotary motion into reciprocating motion. And we want to achieve a good model that can predict the behavior in a range of operating conditions. And if you draw it like this, it's quite simple. But if you then make it in reality, you have all these complex friction and play effects you need to take into account. So the complex part is the friction forces. So we will make a PAN model for it. We'll introduce it quickly. So we assume a simple second order system, which has some inertia, some damping, some stiffness terms. And we augment these three normally constant parameters by making or multiplying them by 1 plus a neural network. So these Z parts here are actually 3 different neural networks. And then we can do a training run and outcome some maps that say for each parameter how it should be not just a constant value. So it makes it a nonlinear model. And then you can analyze these maps to see, okay, how can we now capture this with physics and improve our physical model again? We see that we have actually a good performance, so it can predict quite well, given the torque, what the angle and the angular velocity will be. But I was talking about robustness and trust in the model. So what was that about? Well, we noticed that our system has some randomness in it because there is some play in the joints and in the motor. And also if you use it for a long time, because of the friction, it starts to heat up and then the metal components start to expand a bit and the behavior changes. So this is of course not in our model, this temperature effect. So it is we can consider it a stochastic effect of the system. If we do then similar experiments, repeat the same experiment many times, and we see that there is some variability. And this is then also something we want to quantify. So we can quantify this intrinsic uncertainty this time. And then we can also use the fact that we have quantified it for the following problem. So let's think again about, let's say, a weaving loom. We have to make some kind of displacement motion, and we need to find the torque profile we need to apply to achieve this motion. And we want to go as fast as possible, but we cannot enter the red square. So we need to be at a certain time, at a certain displacement, and then we need to be above that displacement also until a certain time. So we need to be above the red square. And if you have this uncertainty or this variability of the system, if you take the optimal path, yeah, then of course there will be deviating runs that will then violate the constraint. So if we now have quantified the variability in our system, we can, yeah, move up our optimal motion so that the probability of violating the constraints will be very low. So what we have done, we have taken into account the uncertainty in our optimal control problem. And you might say, okay, very good, very nice, but this was all in simulation on the computer. Control problems, they use a model, but they calculate everything on the computer. Did it really happen like that in the real world? And then here on the left, we have what I've just shown in simulation. And on the right, we have here what happened in reality. So here the gray bands are the actual variability, empirical variability, so what we measured. And we see that, okay, they correspond very well. And also, if we now apply our robust torque profile, the variability is also so that it is not violating the constraint. So we see here that the gray is not going in the red square. So we can consider it as a success that our model was able to now apply a robust strategy. So to recap, what did I talk about today? We believe at VanderSmeek that this physics-augmented neural networks approach can leverage your limited data by adding in physical insight or physical knowledge. And I've also talked about uncertainty quantification today, how you can deal with the fact that limited data leads to no trust in your model. Therefore, you have to make that explicit by adding uncertainty quantification, and you can also use it to guide your experiments. So yeah, actually put it here again. So we can incorporate physical knowledge to reduce data requirements. Limited data will lead to uncertainty or no trust in the model. So you have to make it explicit with uncertainty quantification. Or I believe that's a good idea. Model uncertainty can enable optimized experiments. And in our case, and of course, every case is different, but in our case, we could achieve the same error with 60% less data. We used also intrinsic uncertainty to allow robust optimal control, avoiding the violations of our strict movement constraints. So if you find this inspiring, then do not hesitate to contact us. I will try to reply as soon as possible, and then we can see how we can investigate your problems together. And then I will give the word again to Dries.
Okay, thank you, Rob, for the interesting presentation. It's already 1 o'clock, but maybe there are still some people who have questions, so we will handle your questions now. If you have questions, just raise your hand. In the Q&A, I didn't see any, but now, yeah. I'm going to give the floor to El Kafafi. I'm going to allow to put on your mic and your camera. So the floor is yours.
Okay, thank you very much. This is Mahmoud El-Kafafi from Siemens Digital Industry Software, located at Leuven. Thank you very much for your nice slides and explanation. I have a question on the uncertainty quantification
Okay.
Did it get correctly that at the end you are using ensemble learning with a Gaussian process, or is it not? I didn't get completely which technique you exactly using for this uncertainty quantification.
Yeah. So for the uncertainty quantification, we had the model uncertainty and the intrinsic uncertainty. For the model uncertainty, we have investigated two techniques. So ensemble training is where you train multiple networks and then you calculate the empirical distribution of the predictions. So we use that, and then we approximate that for the optimal experiments with the Gaussian process. So, and then we use the Gaussian process to optimize our experiments because it's a little easier to calculate what the improvement on the posterior variance is with the Gaussian process. And then for the intrinsic uncertainty, we use the probabilistic neural networks, which is a fancy word for just predicting the mean and the sigma or the variance of a normal distribution at the output instead of just a 1 point estimate.
So at the end, it's you train like ensemble of neural networks, and you take the mean and the standard deviation. Is this what you mean by probabilistic neural network?
No, so for the intrinsic uncertainty, there's just one network, but it predicts the mean and standard deviation.
Okay.
And then because it's inside all these physical equations, you need to propagate it to the output in order to then put in your data and use a negative log likelihood cost function. But if you want, you can message me and we have some publications about this, how it goes to the technical detail of what we do. So
Okay.
I suggest to just contact me and then I will give you the link.
Thank you so much. Thank you very much.
Okay, thank you, Rob. Any other questions? Not yet. Okay, if there are no other questions, we're going to wrap up. So I'm going to send the presentation to you, the recording of this meeting to you, and a short evaluation so that we know how you have appreciated this Tech at Lunch. So Rob, thank you for your presentation again, and thank you all for being here. Bye.
Thank you.